Hello everyone, and welcome to our fourth haloacetic acids coffee conversation. Joining me again is my ion chromatography specialist colleague Gemma Ellison. Hi Gemma, how are you today?
All good, thank you, Simon. How are you?
I'm fine, thanks for asking. Great to hear that all's good with you as well, Gemma. In our previous conversations, we've discussed why water needs to be disinfected and how haloacetic acids are formed as a result. You've also told us about what regulations and what methods and technologies there are for monitoring these compounds. In today's conversation, I'd like to ask you about the latest developments in measuring haloacetic acids using the ICMS technology you mentioned in our previous meeting.
Yeah, so I think we've almost covered all of our story now on haloacetic acids. We've gone from cholera to ion chromatography with mass spectrometry. So we've covered a lot, and all of the bits in between, the history, the regulations, the methods, and the pros and cons of using two different techniques from two different approved methods. So this will be the last of these chats for a while. So I've got something quite new and exciting to talk about.
All right, sounds very interesting, Gemma. Tell us more.
Okay. So last time we talked about IC with mass spectrometry and the EPA method 557 for haloacetic acids. And we mentioned why ICMS has certain advantages, one of them being sample preparation that just isn't required with IC when you compare it to the GC approved method, where you've got all these steps of derivatization and extractions, lots of chemicals. It takes a long time, and we don't have this with IC. So in turn, it also saves time, but it also eliminates lots of those sources of errors, because when we do lots of manual steps, as humans, we tend to make mistakes. And I think we all want to be more productive. We're all very busy, and if you've got tons and tons of samples, it's going to take you a long time to work through these.
Yeah, productivity is increasingly important for a lot of people in laboratories today, certainly.
Exactly. So, however, I do appreciate that ICMS does sound a little bit scary or complex, and especially if you're new to this technique, it might sound very complicated. And it isn't, basically. It doesn't have to be. Lots of the features of the ICMS are automated. You don't even need to make up your mobile phase, the eluent. It actually is generated online for you within the system. So you just add deionized water. So most of the scary stuff is actually taken care of by the system. But what I really wanted to talk about today is the launch of the validated disinfection byproduct application workflow. And this includes the determination of the HAA9 and bromate and dilapon.
Okay, thanks Gemma. So what is the validated disinfectant byproducts application workflow, apart from being a bit of a mouthful? And what benefits does it bring to haloacetic acid analysis?
Yeah, sorry about the long name there, but it's basically a full workflow of everything you need to analyse up to 9 HAAs, plus bromate and plus dilapon. So dilapon is actually a herbicide, but it's often commonly tested for alongside disinfection byproducts. So the package consists of the Thermo Scientific Dionex ICS 6000 IC system and the Thermo Scientific TSQ Fortis mass spectrometer. And then you get your choice of software, plus the columns that you need to be able to run the analysis. So I appreciate this just sounds like a list of instruments and consumables, but actually it isn't. It's a validated workflow. What this means is that Thermo Fisher Scientific, as well as making all of the products, they actually install and validate and service the complete workflow. So everything is ready, which really speeds up the deployment in your lab. And the methods will be pre-installed, they'll be validated, all to meet EPA 557.
Okay, sounds good.
Yeah, less work to do. So ICMS sounds like quite an investment, and yes it is, let's be honest. If you add a mass spectrometer, there'll always be an increase in initial cost. But what we've estimated is that if you were a lab running 25 or more batches of sample a month, then this method will save money from an operational standpoint from the point of installation. And there's actually a cost saving calculator that you can put your batch numbers in and see if this method will actually save you money in the long term. Now, one of the things with the column, EPA 557 actually has written in flexibility on the IC column that you can use. And this workflow uses the Thermo Scientific Dynex Iron Pack AS31 column. And this is actually shown to decrease the runtime of the previously stated column, the AS24. And the decrease is from 57 minutes to 35 minutes. This column, not only is it a shorter runtime, but it's actually a higher capacity column. So if you're really looking at very trace levels, and previously you might have had to do some pre-concentration to be able to see them, you shouldn't need to do that here. So you can actually use a larger injection loop on the IC system, and the column, because of its high capacity, is designed to handle this.
Okay, that's quite a big time saving you've described here, Gemma. That's also quite a lot of information you've just covered there, so thanks for that. But how would you summarise what you've just said?
Sorry, yes, it was a lot of information. So to summarise it, really, the system comes with a fully validated workflow, which is installed. The runtime is faster using the new column, and there are cost savings if you are working on over 25 batches a month. All of the sample preparation and additional chemicals that we used with the GC-based methods is eliminated. You can separate the HAA9, bromate, and dilapon, as well as the common anions, all the standard tests that are done in a drinking water laboratory. No solvents are needed with the IC, so you're saving costs there, as well as the process of disposing of them safely. And then there's potential to use the IC or the ICMS for other applications done in a water lab, such as anions, oxyhalides, polar pesticides.
All right, certainly sounds like a very effective and efficient approach to me. But how would analysts measuring disinfectant byproducts in drinking water know if this was the right route for them to take in their laboratory?
That's a really good question, and I would say if you were wondering if this workflow is for you, then you could consider the following questions. So is time tight in the laboratory, and are the staff and resources available to perform all of the analytical tasks such as the extractions and the derivations? Do you have the resource to do that? Do you need a reliable technique to reduce repeat analyses? So if there are errors with manual preparation, do you have the time and ability to be able to repeat analysis if there are errors made? Do you have multiple inorganic analytes that need testing? This gives you the flexibility from the other uses for the IC. And would you benefit from faster sample to results turnover times? So I don't know many people that would maybe say no to that, but that is definitely something to consider. And also, are you concerned about the high use of organic solvents and the associated costs of disposing those as chemical waste? And if the answer is yes to one or more of those questions, then it's definitely worth checking out the website thermofisher.com/HAA workflow for more information on how the new validated disinfection byproduct application workflow can help you. So, although this is the last coffee conversation for now, the discussion doesn't have to stop there, and we want to hear from you. So if any of this information has interested you, then you can email us at analyse.eu@thermofisher.com, or alternatively you can click on the link included with this post to request contact from one of our team.
Okay, and that's analyse with a Z, isn't it? It does say it on the bottom of the screen here. Yeah. Okay, great. Thanks a lot for your time again today, Gemma. In this series of conversations, it's been really interesting for me, certainly, to learn about the history of water disinfection and how techniques have had to be developed to monitor the byproducts produced in the disinfection process to ensure that water is safe to drink. So I'm sure it's been extremely interesting for everybody listening too. That concludes today's conversation, and indeed our whole series of haloacetic acid conversations, as Gemma mentioned earlier. So thanks again to Gemma, and also thanks to all of you for listening, and bye for now.
Thank you. Bye-bye.